Hey, welcome back to your favorite calculus class. We're going to take a look at derivatives of inverse functions briefly, and then mostly spend our time with logarithms here. So this is just kind of an FYI here. For this function, if you remember how to find an inverse, y equals 1/5 x plus 7. If we were to find an inverse, we switch those x's and y's, and we solve for the new y. So we have 1/5 y equals x minus 7. Multiply everything by 5, and that's our inverse. So for all points x, y on the first one, they flip-flop for the inverse, right? So if we were to we could graph those together, and what you're going to find, the interesting thing is, for this function, f of x, if I was to find its derivative, I'll call it df dx, it's 1/5, right? And then over here, if I was going to find its derivative, it's 5. Notice, they're reciprocals. They're reciprocals. Here's a picture of the original function, the 1/5 x plus 7. Here's its inverse, and they're as inverses, they're reciprocals about the line y equals x, right? They're reflective about that line y equals x. And then notice again their derivatives. They're reciprocal. They're reciprocals. 1/5. The reciprocal of 1/5. 1 over 1/5 is 5, right? It's derivative. Here's another set of inverses. You got x squared, part of x squared at least, and then if you found its inverse, the square root of x, right? And if you took the slope at the point 2,4, slope's 4. Slope would be the reciprocal 1/4 on its inverse. All right, now for logarithmic functions. Now, if you remember, the derivative, I'm going to use x here. The derivative of natural log is 1 over x. And not if you remember, I'm sorry, we're going to introduce this. So let's go ahead and do the proof here. Why is that? But you know what? Let's take y being the natural log of x, and let's take e to both sides. So e to this side, e to that side. So we have e to the y, e to the ln of x. Of course, those are inverses; they undo each other. So e to the y equals x, and then I'm going to run the derivative on that. And so your derivative, and I'm using the rule that the derivative of a to the x is ln of a times a to the x, right? X right there. Now these variables disagree, the derivative of e to the y, right? I'm taking the derivative with respect to x, so I have to think about that. So that's ln of e to the y, but then it's chain rule on that y. The derivative of y is 1 dy dx. Over here, the variables agree, right? Because that's implicit differentiation on that left-hand side. Variables disagree. Now we know the natural log of e is 1, so that's just 1. So now I'm just solving for. So I got 1 e to the y dy dx equals 1. So now solve for dy dx. So I get divide by e to the y both sides. So I have dy dx is 1 over e to the y. But if you remember, what was e to the y? E to the y was the same thing as x. So by substitution, that's 1 over x. So there we go. Hence, the derivative of the natural log of x is 1 over x. Let's do some problems with it. Now, we have to apply the chain rule if I've got a composite function. I don't have the natural log of just x. I have the natural log of 2x. All right, this is the rule with no chain rule. So this becomes 1 over 2x, but then I take the derivative of 2x. I take the derivative of the inside, which is 2. So this one just ends up being 1 over x. This one, when I take the derivative, it's 1 over that stuff, x squared plus 1. Chain rule on that, because I don't just have an x inside there, chain rule on that is 2x plus 0. So this ends up being 2x over x squared plus 1, right? Here we've got the derivative of x times the natural log of x. So I got the product rule, derivative of the first times the second plus the first derivative of the second. So we got ln of x plus x over x. Well, x over x is just 1. ln x plus 1. Here we've got the power rule. I've got to run the power rule first. So this becomes 3 ln of x squared, but then I got chain rule because I don't just have an x inside. I got the natural log of x, so I take the derivative of the natural log, which is 1 over x. So this just becomes 3 over x ln of x squared. Okay. This we reminded you about already. I always think of it as just in terms of a to the x, and then if I have to apply the chain rule, I do, right? Now, what about the log base a of u? Now, remember, so the rule we're trying to come up with is the derivative of log base a, and I'm going to use x here. Log base a of x. Okay, according to the rule, I'm going to write this another way. This is 1 over ln of a times 1 over x. Okay. Now, the reason is, remember, log base a of, I'm going to call it x. This is the same as the ln of x over the ln of a, right? So, if I was taking the derivative of the ln of x over the ln of a, that's the same thing as taking the derivative of 1 over ln of a. That's a constant right there. That a is a number times the ln of x. So the constant stays there, and then what's the derivative of the natural log? 1 over x. That's why it's 1 over ln of a, 1 over the natural log of a times 1 over x. Okay, that's because you can use that change of base formula. Okay, so don't forget these. All right, don't forget these. So derivative a to the x ln of a times a to the x. Our other one we're using is 1 over ln of a times 1 over x, right? Alright, so dy dx here. Dy dx is ln of 2 times 2 to the x, and there's no chain rule on that. This one does have a chain rule. This is a composite function. So we have ln of 2 times 2 to the 3x. It's not x up there, it's 3x, so I got to use chain rule 3. So that becomes dy dx is, I'm going to put 3 ln of 2 in front, and then 2 to the 3x afterwards. Okay? Alright, this one, dy dx. So now I'm using this rule. So I have 1 over ln of 10, 10's my a there, times 1 over the x, that's the cosine of a. Now it's not just x there, it's cosine x. But now it's chain rule because it's not just x there, it's cosine x. So I got to take the derivative of the cosine, which is negative sine. So we've got 1 over the natural log of 10. I'm going to take that negative out front. And then times sine over cosine, or negative 1 over ln of 10 tangent of x. Same thing. That's your dy dx on that. Alright, let's do some more here. Dy dx, we got ln of 3 a to the x, but we don't have just an x up there, we got to take the derivative. So this becomes dy dx is negative ln of 3 to the negative x. Alright, how about this one? dy, now it's not x, it's dy d theta here. So 1 over ln of 2, 2 is our a here, times 1 over x, but it's not x, it's 5 theta. And again, there's chain rule, so derivative of 5 theta is just 5. Derivative of 5x is 5, right? Notice our 5's cancel. So this becomes dy d theta is 1 over theta ln of 2, or ln of 2 theta. All right, make sure it's theta times there. All right, last one here. We've got y equaling log base 4 of x plus log base 4 of x squared. So dy dx equals 1 over ln of 4 times 1 over x. Chain rule on that, derivative of x just 1. Plus, now I'm running the derivative of log base 4 of x squared. So 1 over ln of a times 1 over x, but it's x squared in this case, and so I got to run the chain rule 2x here. So I got 1 over x ln of 4 plus, now notice one of these x's cancel, so 2 over x ln of 4. So now I've got a common denominator. So dy dx, 1 plus 2, I got 3 over x ln of 4. Alright, well, thanks so much for listening. That is your derivatives of your logarithms and a little bit on inverse functions as well. You guys have a great day.